Hi everyone, I'm Yuchi, coming from University of Michigan. My advisor is Professor Kang Shin. Today I'm going to present my latest work called EchoTag. That is a kind of mobile system can enable everybody's phone to remember location pretty accurately. So let's start from talking our motivation to design this kind of system called EchoTag. You just imagine one day, when you come back home, you feel so tired, so you're just walking directly to your bedroom. You find a box called music. That's the box called music. You put your phone onto the box, then your favorite songs will be streamed to your audio system automatically. If you plan to go to sleep, you just slightly move this box, then move your phone to another box called sleep. Then your phone will know that and turn into silent mode in case make any disturbance to your sleep. If the lighting system of your house is connected, it can also turn off the light for you. So computation in this way is generally known as context-aware computing or indoor geofencing. Based on our survey, more than 30 users, we found that most users really like this functionality. And after they try our system, they believe the performance of our system can support this functionality. People really like this functionality because they think it helps them to save their time to find the target application. And the natural combination between this box and the phone's application help them to find the things to do. So now we know how promising this application is. The next question we are going to ask is if the system we have right now can support this functionality. I will mainly categorize the system we have right now to sense the location to two categories. The first one is the infrastructure-free technology. Most of this technology, they rely on to monitor background signal noise, such as you can use your Wi-Fi, you have this avian signal, you have this geomagnetism, or you have this audio noise from your air conditioning. The second group is called infrastructure-based, which asks users to deploy additional sensors around the building, such as you have this sonar sensor, or you have this programmable LED, or this Bluetooth iBeacon. So generally, technology in the first group is nearly readily to be implemented in your phone because they don't rely on these additional sensors. But unfortunately, the sensing resolution, the sensing error is usually meter level or above. Just a very few of them can support 30 centimeter or higher accuracy under certain environment setting. So generally, the next group of technology can support you more finer resolution. That will be the potential interface to support the functionality we talked so far. But you will find the second group of technology that asks users to deploy the additional sensors, not only about the cost to buy these sensors, but also a lot of effort to deploy this sensor, to calibrate this sensor. So make this kind of technology less attractive to the user, especially for personal usage. So we start to think about one question. If there is a system that can kind of strike the balance between the low cost and the high accuracy, the answer is a system that we proposed called EchoTag. The idea is that we use this actively sensed acoustic sensing and to remember locations of a phone. EchoTag can give you this fine resolution and just based on built-in sensors. Okay, so EchoTag can give you this fine resolution because we provide the sensing actively. That means we don't rely on the signal in the background, such as we don't rely on the audio noise from your air conditioning because that kind of noise is not reliable. It's not controlled by your phone yourself. Second, EchoTag can give you this high resolution based on just a limited overhead. What I mean here is just rely on built-in sensor because we mainly use the acoustic signal. The same technology can also be applied to other signals such as Wi-Fi, but we choose to use the acoustic one because that's nearly readily to be implemented in the phone. So because we only need a microphone and a speaker, which is pretty general on a smartphone nowadays. The way to use EchoTag is quite easy. You just find a location. Interestingly, you use this pencil to draw an outline of your phone, and you trigger our application to sense the environment. You get this reflection, so you select the target application to be combined to that location. After this setting, you just put your phone back to that location, and the application will be triggered automatically. So there's one interesting I would like to mention here is that this box is drawn by the pencil. It's just used as a reminder for the user to remember layers tag and how you put the phone back to the tag to trigger the application. It's not necessary to be this drawn tag by the pencil. It could be anything. For example, if you found some service, a break service, so you are unable to draw on the table, you could also get some of this memo pad, cut it to a shape of the phone, or attach it to a service you want to sense, you want the phone to remember. So let's talk about how we design a system called EchoTag. I will start from introducing the most important component called active acoustic sensing. The idea is, if you find a location you want the phone to remember, you just put the phone to that location, trigger our application to send a series of spatial designed sound to the environment. Because the environment to the location is different from location to location, so you will get a very unique acoustic response at that location. After you get it, you do some further processing to get the signature. In the same time, EchoTag also recorded the Wi-Fi and the tiered, which just uses some optimization purpose that I will go into talk later. So when you want to recognize some location, you put the phone to a new location, you trigger our application, get another round of the sound. Then by comparing this new created sound response from the environment to the saved one, EchoTag can understand if that is a tagged location or not, and what application should be triggered. If it's possible, EchoTag will also update this new corrected feature to our database for future reference. So as you can find in this figure, the most important part for EchoTag to remember the location is this acoustic response from the environment, which is also called the acoustic signature. So what is the cause of this acoustic signature? In this presentation, I will give you a very simplified example to illustrate the idea of this acoustic signature. That is, we assume in the environment, there is just one table. You put the phone on the table, and around the edges of the table, there are two obstacles. It's kind of the main source of these reflections. In the real environment, this obstacle could be anything. For example, if you press the tag here, this reflection source could be that wall, could be this ceiling, or even its projection screen. But in this example, we just assume there are only two sources of reflection. So when the phone plays the sound to the environment, it will get a reflection from these two sources of reflection. And because the distance of this phone to those obstacles is different, the reflection arrives at the phone with a different delay. That makes how the reflection receives the phone will become very different. For example, at a certain frequency, because the delay, the signal of reflection will be combined destructively. At the other frequency, the signal will be constructed constructively. How the signal is combined at a location is pretty unique and different from location to location. For example, if we slightly move this phone to the right, and you will find that the delay of two these reflections is changed. Thus, how the signal is combined is also changed. In this new location, the signal at frequency 1 is combined constructively. If we draw the correct reflection in the dimension of amplitude and the frequency, you will find that's the signal we send by our phone, and that's the reflection we get at the first location, that's the reflection we get at the second location. So in summary, EchoTag is trying to use this decay of reflection. In wireless, it's known as a multi-pass fading, frequency selective fading, but we use this property in the audio signal to identify the location. We also make the our audio processing try to improve the performance of EchoTag. I will not mention that too much. Most of this detail is included in the paper. There's only one thing I would like to mention. It's about how do we choose the amplitude of the signal we send, because I think that's simple and pretty interesting to demonstrate the benefit of the active sensing. So let's look about amplitude control of the EchoTag. But before that, I will show you that's a signature we use in the EchoTag. So as you can find here, we plot this signature collected at one single location with a signature between the 11 kHz to 22 kHz. With a left channel signature, right channel signature. We plot this signature over time to show how signature changes over time. So remember what I said, how the signal is combined. It's used as a signature in the EchoTag. In this figure, that means this bright vertical line, or you can see there are some vertical darkened line. But as you can also find in this figure, if we play the signal we send by ourselves by the phone in the full volume, then the signal is not inconsistent over time, because most of the signal we received by the microphone is actually saturated by the signal sent directly by the phone, rather than the reflection we want collected from the environment. So there's one way to mitigate this problem, is that we lower the volume down to send the source signal. And then you can find that if we lower the volume from 4 volume to 1% of the volume, the signal is no longer saturated by the signal sent directly by the phone. But we get another issue. That's the signal to noise ratio is too low to make this signal reliable over time. So in our setting for the Galaxy S5, the base setting is about 5% volume. That gives us a pretty perfect, pretty beautiful bright line and the dark line here, pretty consistent over time. So I would like to mention this interesting design here because that shows the benefit of what we call the active sensing. The signal is sent by the phone rather than we collect the background signal. So we can design the signal at any phone we want. In this example, we show that how we change the amplitude of the signal. In the paper, we also mention more about how to choose the length of a signal, what the style of a signal, how many times you should wait for the signal to get another round of the signal correction. And that's the way make EchoTag can give you this very fine sensing resolution with just a limited overhead. Okay, so now we get this signature. How to classify? We put the correct signature like this into the supported vector machine. More specifically, what we put is the one against the all multi-class SVM. The idea of it, if you assume there's a multiple location, you will have multiple classifiers for each location. That is used to identify if the tag location is identified. And we also have one more additional classifier. It's called the no tag classifier, which is used to identify if there's a tag here or not. So here's a simple example. Assume you have 2 locations to identify. That is location A, location B. So as what we said before, we will have 2 classifiers for these 2 locations. And we also have one more additional no-tag classifier. If the data is collected at a location A, you will find that that's the output probability for these 3 classifiers. It's very clear that you can set a threshold here. If you set a proper threshold, the EchoTag can identify this data is collected from location A, not location B, or there's no tag. So the same principle can be also applied to different data from different locations. We also make some further optimization. The idea is to try to reduce the number of chances to trigger our audio sensing environment. The problem is that if we do that too much, it causes too much energy and a little bit of annoyance to the user. Even though it's nearly inaudible, remember the frequency we use is between 11K to 22K, but it's still audible for certain users. The way we try to do it is we use the Wi-Fi beacon and the tiered. So it's like a two layer of localization. There's a cross layer, which is used to remove this overhead. We use this tiered match and the Wi-Fi match to remove unnecessary trigger of this audio sensing. For example, I will show you the tiered profile we created. When the user is walking, is sitting, and is taking out his phone, putting the phone into the box. So that's the only spot that's the timing we need to trigger the audio sensing to know if that is a tagged location or not. We use this technology kind of saving about 80% of the overhead energy consumption overhead of EchoTag. The further performance evaluation we're going to be shown here. To evaluate the system, we implement a kind of 2 versions of EchoTag. It's an offline version that we use mainly in this evaluation. There's an online version used for the usability study. So we do the EchoTag, we evaluate the EchoTag in these 2 environments. That is a pretty typical office environment, and there's a home environment. The circled areas indicate the place we deploy this tagged system. That's a tagged system we deployed. There's a disjoint tagged system used to identify the baseline performance of an EchoTag. There's a overlapped tagged system that is to test the maximum resolution of the EchoTag. So in overall, we can have multiple data sets from the home, from the office environment with different tagging system and with different time span from 30 minutes to 1 week. So I will give you a summary of our experimental result. More detailed results included in our paper. In summary, first of all, the most important thing is about the sensing resolution. The sensing resolution of EchoTag is about 1 centimeter in 30 degrees. That means that if you separate the tag about 1 centimeter away, then the phone can identify it belongs to another tag. The false positive is about 3%. We define the false positive as the EchoTag give you a wrong location prediction divided by number of audio sensing. So based on our experiment, when people carry the EchoTag in your daily life, it's about 2 false triggers per day. The accuracy for EchoTag is pretty decent, especially for the 30 minutes, that's a short time period. You will see that for the office environment, the home environment, it can give you the accuracy more than 95%. But the EchoTag actually gets some problems in the long time data set, as you can see here in our paper, especially it happens in my home environment. Mainly, I found that most of this detection error happened in my kitchen because my wife is unaware why I'm doing this experiment. So she cooked at the kitchen, keeping moving around the big cookers, make the environment change. And we found that's true. In certain environment, if you want to deploy the tag, you should take care about the environment change. If that happens, the only way you can do is that you need to make the phone to know how the environment change. So we decided to collect the data more than 1 day to see if the EchoTag can identify this environment change. The result is mostly positive. That is, we consecutively to get the training data for the first 4 days in my kitchen. Then we use this 4-day data set, which include the movement of a cooker made by my wife. And we can see that the accuracy is increased from 50% to more than 90%. We also, remember we do the optimization to record our sensor data to try to reduce the chance to trigger audio sensing. So we also use the other sensor data, such as geomagnetism, such as Wi-Fi SSI, try to see if they can differentiate this location. Our result is about, if we just use our sensor data, the accuracy is less than 20% in the same scenario we tested here. So now we know the environment change can affect the performance of EchoTag. So we also test the outer environment change with the addition of a different object. For example, the way we do it is that we put the tag here, we train the tag, we try to make the prediction. During we make the prediction, we add additional object to the environment. So not surprisingly, we found a small object like your marks, like your hands, doesn't cause too much trouble to EchoTag because the reflection from this small object is not that significant. But surprisingly, we also found that the human body is also resistant to the EchoTag because the material of a human is more prone to absorb the signal rather than reflect it. We also tested the placement error that can be tolerated in EchoTag. That's defined as if we have a tag system here. How many displacement error you can have the user to do, but the phone can still identify the tag. So that is about 4 millimeter. It's pretty stringent, which matches our mathematical model. It's about 1/4 wavelengths. We make our experiment usability study in the following slide. Okay, so I guess I run out of time. I will just skip most of it. But we've also found that if you really want to increase this limitation, you can use a different setting of EchoTag, which matches our mathematical model. We can introduce this to 1 centimeter with different sensing frequency. We have some usability study. We mainly recruited a student from our building. We asked them to try the demo version of EchoTag, and they give us our feedback of their how the performance of EchoTag. Most of the feedback is kind of positive for EchoTag, not only about the performance, but also such as the noise is acceptable. Actually, most people didn't notice about the sound we used until we asked them about how you feel about the noise. And in terms of application, most people think that the EchoTag can support this application, and they think this application is quite useful for their daily life. So in summary, EchoTag is a system that can make the phone to remember location. So it's different from the other localization. It cannot give you an absolute XYZ. It can only help you to remember location. That give you a very fine sensing resolution, high accuracy, very low overhead, and the prediction delay. More importantly, it's pretty easy to deploy in the existing mobile phone system. Thank you for your listening. I am glad to take any question.
Thank you, Yuchi.